Welcome everyone to Talk 2 of our technical webinar series, Tech Talk. Today we focus on how OTN Technologies is incorporating new capabilities to meet the emerging network challenges. Our speaker, Dr. KJ, is the Vice President Technology and is a part of the team that sets the tech strategy at Tejas. He holds a PhD from UC Berkeley and a BTech degree from IIT Kanpur. As a principal investigator in Bell Labs research, he worked on several projects which involved VLSI devices. In 2000, he co-founded a startup in the US working to develop a high-capacity core router, which was acquired by Telecom in 2003. KJ joined Tejas Networks in 2005 and currently works on new growth areas for the company. Over to you, KJ.
So thanks everybody for joining, and we would like to get questions at the end of the seminar. So I think we'll budget about 45 minutes for the talk and leave some time at the end for questions and answers. Really, the main goal of this talk is to introduce people to optical transport network technology. We'll go through a brief introduction of what OTN is, talk a little bit about the technology features and the use cases. This is the most interesting part. And finally, I'll wrap it up in a slide with what are the key takeaways that you probably should consider from this talk. So like Hema said, at the CTO office, we look at multiple technologies, and OTN is something that we've been looking at since a while, since some time. One of the reasons for us to look at OTN and other technologies is the basic structure of how a multi-operator telecom network works today. So here, what we are depicting is a number of different carriers, and typically even within a carrier, they may have sub-networks which are made with another vendor's equipment. So when a carrier B has to offer a solution to two of its customers, he may not have a footprint directly connecting to those end devices. So he has to use some other carrier's network. Give me a second. So he'll have to hand off traffic to carrier A and to carrier C in order for the two endpoints to connect. And even within his own network, he has a challenge of essentially connecting vendor one's equipment to vendor two equipment. So this end-to-end service, for it to work, there needs to be well-defined handoff, not only within the vendors, inter-vendor, but also inter-carrier. And we need a view. If this service is down, carrier A needs to be debugged to be able to debug his part of the network. Within carrier B, the EMS of vendor one will debug this section. The EMS of vendor 3 will debug this section. The overall umbrella EMS, NMS that carrier B uses will establish that the service works between these two endpoints. So that's essentially how today large-scale networks are built, and the responsibility of making sure that there are standardizations is left to the International Telecom Union, the ITUT, and they have essentially standardized various interfaces, primarily SDH Sonnet, because that was the primary voice-based services that were there in the latter part of the previous century. So the SDH was a standard handoff interface, and that was designed around fixed time frames. We all know voice has 4 kilohertz bandwidth, that is 8 kilosamples. And so that basically gives you 125 microsecond for a sample, right? So that's essentially where the 125 microsecond frame time for SDH Sonnet came. And that had worked well in the last century, but early in this century, it has lost its momentum. And the key reasons to do that for that was that SDH Sonnet was based on containers that were relatively low capacity, 2 MB, 45 MB, and going up to 10 gigabit rates, right? And these were statically multiplexed, right? I've put statically because this is fixed multiplexing as opposed to in packets network where it is statistical multiplexing. So these are static circuits that are defined. Now, what happened towards the latter part of the previous century is that data became the important currency. Even voice was transitioning to voice over IP. And the technique people used was to carry data by mapping it into multiple TUs. And this was okay when you had to offer, let's say, 100 megabit service. You could take maybe 2 VC3s and sort of use them for about 90 megabits of service. But as you went to gigabit rates, the number of tributary units that you had to combine to get to be able to carry your client signal was too many. And so it was rather cumbersome to carry high-speed data over SDH networks. There was another issue that started coming up towards the end of the previous century when 10 gigabit was the currency, that as you scale a 40 gigabit signal, the amount of data in a 125 microsecond frame was becoming very large. And so the framing structure and the kind of bit interleaved parity schemes that were there in the SDH Sonnet framing structures were not really effective in terms of telling you that there had been an error in the frame. In any case, there is no real way for you to retransmit. So your transmission layer was starting to feel the effects of a very large frame size resulting from a fixed time frames. And another issue that operators were running into when things were national, it was okay. But as you went international, all these SDH networks had to be synchronized because that's basically synchronous digital hierarchy. And so timing was, and sort of making sure that things and the bit slippages were in check was a little, was a problem that needed to be solved. And furthermore, what I had showed in the previous slide that you needed to have multiple levels of connection monitoring was there in the standard, but it was relatively complex. And so all of this really made SDH lose the momentum. And then the ITUT had no other sort of mechanism for handoff. And they decided that, okay, we will take up these challenges and work with define a new standard based on fixed size frames. And I'll tell you how that helped things. So the ITUT then sort of came up with a standard to cater to the larger, today's higher rate digital services. And the idea was that the network could then evolve to higher bandwidths and essentially try to do as much switching at the optical layer and try to get low latency services across the globe. So it defined a new optical transport hierarchy, and this time they took a conscious decision to define the management of optical channels in a multi-wavelength optical domain and the different bitrate framing structures. And most significantly was the fact that the framing structure allowed for a forward error correction field inside it. You realize that as the data rates go higher, the chances of a bit error increase because the I of the signal, that the time is smaller and smaller for every bit instance. And so the precision with which you need to sample the signal becomes higher. So the error rates generally tend to increase as we go to higher rates of signaling. Even with better modulation and all of that, the very fact that you need precision in sampling the input waveform means that your margin of error is higher. And so but you cannot really have inefficient transport layer because all higher layers performance characteristics are derived from the performance characteristics of the lower layers. An analogy is that if your road is not good, you can have the fastest car, but if there are bumps and if the road doesn't allow for high-speed movement, then you cannot do anything to alleviate that. So given that the optical layer is the lowest layer in the electrical hierarchy, it really needs to have very good characteristics. So it cannot introduce errors, for example. So the need to have error-free transmission over longer signals was very critical to the emerging growth of optical networks. So that's really what they were aiming at. And obviously they want all the benefits that were there in SDH, the ability to carry low rate signals, the ability to build a network and have it run without a very large trained workforce, the reliability that a transport style network provides. And one of the key elements was the signal fidelity. I will touch a little bit on this later in the talk, but what you want is that the client signal should be unchanged in terms of its traffic characteristics as it traverses the transport network. I already talked about forward error correction to get longer spans, and they wanted to have a framing technology that could scale. By having a fixed size frame, you can go to higher and higher rates, and it's the frame time that reduces, but the frame size and all the characteristics of error detection, error correction, the path OAM, none of that actually gets affected. So that was very significant thought, and that's basically what gave rise to this very large growth in traffic. So this is just a slide to basically tell that the volume of traffic is sort of growing very steep, and the main consumers of this are more internet users, more devices and connections, faster broadband speeds at home. A lot of this really on the back of a lot of video-based lifestyle that we today have, right? A lot of streaming content, a lot of video calls, normal modes of communication, which were primarily voice-based, are now data-based, data primarily being very little part being messages and a large part of it being videos and images, right? So there's a big need for bandwidth to be scaled, and OTN technology was really the way forward. I just wanted to put up this slide. A lot of people focus on G709, which is really the basic framing structure in the OTN world, but there are other aspects of the network, and I would sort of encourage you to take a look at some of these, especially the standards related to protection, some of the performance and jitter requirements that are there. Reason I'm bringing these out is because OTN has a concept of timing transparency. And that really helps alleviate and meet some of these performance requirements that are there. Similarly, what are the management aspects of an optical transport element? What kind of operations you can do, and what kind of troubleshooting you can do in the optical network is all sort of part of this complex, large set of standards that are incorporated as vendors produce optical networking equipment. For those who are not familiar with OTN, I thought we'd put this slide, and let me just hide this. There are three main parts of the OTN frame. The most important part is obviously the payload, but what's also important is the overhead to make a optical transport unit. So the entire thing is called an optical transport unit. Within that, there is an optical data unit, and there is an optical payload unit inside it, right? So the optical transmission unit includes the FEC area that is protecting the optical data unit, and the optical data unit has some overhead to make sure that we can track various aspects of the payload that is being carried. So that's essentially a broad overview. The frame is about 16,000 odd bytes, which is not very large and not very small. You can fit about 6 or 7 Ethernet frames, 8 Ethernet frames or so at around 1500 bytes a frame. So around that, about 10 Ethernet frames at 1500 bytes you can fit there. So I think it's reasonable size. The different parts of the frame we had talked about. It all starts with the frame alignment, right? So you cannot have a framing structure where you don't know where the bit stream starts, right? So the frame alignment structure is what tells one OTN frame from another OTN frame. And this has ability to not only demarcate a frame, but also multi-frame. So when you have to take a number of frames together as a unit, you can know which count you are at. And then I had talked about the OTU overhead, which basically monitors the optical transport unit, this whole unit. And then the optical data unit monitors the path. And within the optical payload unit, there is overheads, which essentially tell you how the client signals have been mapped into this area. There are a number of different mapping techniques for constant bitrate traffic, for packet traffic, and you need to know what scheme is being used before you sort of look at the contents of the ODU. So that's part of the optical payload unit overhead. And once you put together all of this data, you protect it with some forward error correction so that even if there are some bit errors in transmission, not only can you detect it, but you can correct most of them, right? So I think that's really important. And when you cannot correct the bit overheads, then you start raising alarms saying that there are things that are wrong. And those alarms are indicated in this part of the frame, right? So you have essentially, you know that there is an alarm. So if there is an alternate path, you can try to switch to that, right? So I think this is important in a transport network because any impairment in the transport network needs to be known to the higher layers so that they can be take corrective action. OTN has evolved. It really started with a way to carry STM1416 signals and STM64 signals in 10 gig DWDM. But then as DWDM started to evolve and people started to think of 10 gig lambdas, 40 gig lambdas, essentially that was the time that in the 2010 timeframe. Then later on, 100 gig lambdas and OTU4, essentially a 100 gig payload unit got introduced. And beyond that, over the last few years, people have been working on improving the kind of OTN structures that are required to carry 100 gig and N of 100 gig flexible OTNs, all essentially aligned to the WDM kind of infrastructure. So we saw that DWDM evolved from 2.5 gig to 10 gig lambdas, from 10 gig lambdas, 40 gig really didn't take off, and people went to 100 gig directly because Ethernet generally tends to jump in tens. Although beyond 100 gig, it's been sort of additive in terms of hundreds, 100, 200, 400. But that's sort of what things are, doubling of the bandwidth. So you can see OTN today carries primarily high rate signals. We don't really talk of carrying gigi signals anymore because we have 100 gig lambdas, and aggregation of gigi signals into 10 gigi signals is a relatively inexpensive operation in the packet world. So I think that's basically where 10 gig has become the currency in modern day networks. We do have places where we have now 100 gig, 200 gigi. People are talking of flexible Ethernet, OTU4, which is a 100 gig OTN signal as a handoff. So a lot of the clients today get multiplexed or switched to other OTU signals, and these get carried as lambdas, right? So OTN really catered towards 10 gig lambdas. OTN1, OTN2 had place for 100 gig, but really today we are talking about flexible OTN because we are using, in DWDM, we have started using flexible grids, and the high rate signals are no longer, can no longer be fit into 50 gig ITU grid, and we need either multiple grids or we need fractional grids. So all of that is what's sort of driving the optical network evolution. There is flexible and fractional mapping. There's mappings defined for 25 gig, 40 gig signals. One of the interesting things that's happening is OTN in its original form had a fixed Reed-Solomon code, but today there are different choices with different error correction capabilities that provide you gain in terms of the signal to noise ratio that you can achieve. So the idea is that as optical signal deteriorates over distance and with speed, if you have a certain, without forward error correction, there is a certain reach, but with forward error correction, you can increase the reach because you can correct the errors and have a slightly more impaired optical signal. So what you lose in optical signal to noise ratio, you can make up with some of the digital forward error correction. So that allows you to put your amplifiers a little further to be able to use fewer elements to cover a certain distance. So I think all of those are things that as technology evolves are toolkits that is being introduced, and a combination of what you can do essentially determines the flexibility of the product that you're offering, right? So the more features you can offer, the better your chances of your products being taken up by the operators. One of the things that was important in OTN was the need for ultra low transport latency. So I had mentioned earlier that the frame time in a SDH frame was 125 microseconds. So no matter what you did, you had to wait for the frame to know whether there were errors, whether the data was reliable. And this really didn't work when you had the need for low latency, right? You want to have applications, especially in the financial markets, where every microsecond is important, every nanosecond is important in terms of the trading. So the data had to be sent with ultra low latency. And so this is something that OTN was specially suited for, because as you get to higher and higher rates, your frame time gets lower and lower, right? So you can reduce even though you may have very less data, but you can send it on a high-speed pipe. So that's really where some of this came. The other thing that OTN worked well, especially with this kind of flexibility in terms of how much bandwidth, what application can take, is that you could then start partitioning your network and have dedicated resources so that you weren't worried about some other application or essentially eating into the bandwidth or causing jitter to your service. So this is one of the benefits that I said I'll talk about, that the determinism, when you put a signal into an OTN frame, it is not really affected by the other signals that are occupying the fiber at the same time. So I think that obviously in a WDM perspective, the lambdas are different, but even within that, you have the isolation between different OTN pipes. So that really makes sure that you have guarantees on the network performance. And that's important to several applications which cannot tolerate a high amount of jitter. Obviously, your WhatsApp and your basic applications are not the kind of applications, but if you were doing any kind of industrial control or any kind of application that required interaction, it's very critical that the latency be not only low, but it also be very predictable. This is just a slide I have for completeness. The black really represents the original motivation of OTN, where things were defined for 2.5 gig, 10 gig, and 40 gig rates. And then later 100 gig was added, and the ability to cater to a lot of data. So gigabit, other types of MPLS data, 10 gigabit, 100 gigabit, all were motivations to add additional capability in the multiplexing structure. So in a 10 gigs, you can carry, for example, 8 gigabit Ethernet frames. The original 2.5 gig STM, you can carry 4 of, and obviously you can carry a different number, arbitrary number, if you have them as GFP encapsulated flexible interfaces. So that was an important aspect. This flexible mapping of traffic into the OTN container, this is supported at 10 gig rate, right? Beyond 10 gig, you expect that the pipe is relatively full and you just use static multiplexing till then. But below 10 gig, you have an ability to carry different types of packet bandwidth, right? So that was, it's similar to, I guess people who know SDH know about virtual concatenation, where there are complete paths in the network that can be concatenated. ODU Flex is similar, but it is the one constraint is that it's a single container, but it cannot be split across multiple wavelengths or paths. And thereby the management of this becomes simpler than that of VCAT. In VCAT, the differential delay that you had to support was very high, but in ODU Flex, you don't have that kind of problem to solve. And it would be an extremely tough problem to solve at very high rates in any case. So that essentially becomes a little simpler. There is a way for you to increase and decrease the size of the ODU Flex container, and that's basically called hitless adjustment of ODU Flex. How? And you can essentially size the connection, and you can also size the bandwidth that's being mapped to that. The only sort of, I would say, is a little bit of a drawback is that in a multi-vendor situation, it's a little complex, but nevertheless, it's one of the items in the network planning toolkit that you have if you have to support a customer with sort of where the bandwidth demands are incremental. So you can use this kind of technology. I really wanted to, I think the main focus that we wanted to do is, okay, there is this technology. What do we do with it, right? Where is it sort of useful? And essentially try to show you what features of this technology are important in the different use cases. So we'll first start with the data center interconnect, where you have essentially multiple data centers, and you are trying to interconnect them. Typically, you do that over 100 gig, or now with sort of higher speed interfaces being available, 100 gig, 600 gig. So what's important in this is to essentially do low latency and to provide granularity of service. So because for the web scale companies, I think everything is in terms of 100 gigabit, but still there are a lot of cases where data centers of a customer may require multiple of ODU Flex containers. So that's something that's important. What's another thing that sort of goes along with the data center interconnect is, one is a point-to-point interconnect, but you can also do terabit OTN cross connects. And today we can do OTN switching at terabit rates and going up to 48 terabits. Type of systems have been developed. So there's a lot of switching capacity in the network. You put in your signal, and at the end of the cloud, you deliver it to your customer, right? So that's essentially the data center interconnect. What's important in this is there are two types of encryptions that you can do. You can either do the encryption at the client layer, and essentially what you do, whatever packets were there, you put it in an OTN container and you encrypt the container. And then you essentially multiplex it and carry it over a higher capacity signal. Some of these would be delivered to customer A, some of them are delivered to customer B, but as this OTN signal traverses the network, the client data is secured at the edge of the network, and there is no reason to decrypt it or have any kind of key exchange or a key management problem here. The key management and key exchange is done only at the customer location. So this is essentially something that is very attractive, because as you are trusting your data into the network, you want to make sure that it is protected. There is another approach, which is more of point-to-point, where essentially you have, rather than take all the data and encrypt the individual OTN channels, you actually map it, and then you essentially encrypt the final lambda that you are sending out. But this really works only in point-to-point. It's useful in certain applications, primarily where a lot of sensitive data is to be exchanged between, let's say, a primary data center and a backup data center. So this kind of point-to-point encryption really does the encryption of the entire frame after multiplexing. Obviously, the overhead processing and FEC gets added and then sent out. So these are the two types of secure data center interconnect solutions that you have. You also have the ability to do restoration with GMPLS. So one of the things that the optical networks are known for is protection, but there is also restoration. So when you talk about 50 millisecond protection, you are essentially have a dedicated path, but you can also have an ability to compute the path using a GMPLS control plane running either at the DWDM layer, which is aware of the physical impairments of a link, or at the OTN layer, which is called L1 GMPLS. So you can have various types of services either unprotected at the GMPLS layer, or if one path fails, then automatically another path gets computed and pushed into the network. You can have a protection on the first failure and a restoration on subsequent failures, or you can have protection indefinitely. So all of these are applications. I just wanted to show this in terms of a diagram, where essentially when the first path comes up, then you find another path, and then you essentially keep doing that till there is a viable path. So the only point I just want to make here is that when you are restoring at the OTN layer, you're running a control plane, computing a path. You can sort of do it in around a second. But when you're doing it at the DWDM layer, you also have to make sure that there is appropriate power balancing and certain other actions that have to be taken to make sure that your DWDM link is fine. So it takes a little bit longer to restore the session, but it is definitely better than having no protection in your network. Another place that we are seeing a lot of interest from the operators is to make sure that no matter what the end service is, that the access network is running OTN. So I had said that OTN at 100 gig today can carry a number of different 10 gig services. If customers want 40 gig, they can get that mapped into the same ring that they have. And if there are broadband access or a number of enterprise services that need, let's say, 3 gig, 5 gig service, you can use ODU Flex to essentially deliver those services. So an edge box that is capable of OTN on the uplink and support a number of different client interfaces and client technologies is something that a lot of operators like. And once they come out of these edge boxes, they can go into a larger OTN backbone and essentially carry that traffic towards the routers, and from there on to the end user applications over the internet. One other approach that we see some of the operators use is to build a larger capacity transport network without having to invest a lot of money in expensive router ports. So this is something where the motivation is, rather than switch every packet that goes from the edge routers to a larger router somewhere in the core, you can essentially just carry the OTN. The router gets mapped into the OTN and then gets routed to the larger core routers. So essentially you can, the traffic that is not destined to this location needn't be sort of packet switched at this layer. It can be just OTN switched. So that's the motivation. Everybody is interested in 5G. 5G is, in my view, quite a complex technology, and it's also not clear what are the first use cases. I'll just put this slide to essentially introduce some of the places where OTN and DWDM have been sort of conceived in this architecture. There is something called front haul, which is essentially from the electronics to the antennas and the radio units. So you can think of this as a radio unit, which essentially has the power amp and the other signals used to drive the radio signals. That can be over OTN or DWDM. There is a standard called CIPRI that is used in this domain. Then in terms of 5G, there is talk of a distributed unit and a centralized unit. The distributed unit is really more of what's closer to the PHY and the MAC, and the centralized unit does higher layer functions. There's also talk of having edge computing as part of the 5G network, so you don't really have to go very deep into the core to get the benefit of certain functionality. All of this is really emerging. OTN does deliver the kind of latency and the PTP synchronization that is required for 5G. People are talking of network slicing. I will talk about this also in the next slide. And on the front haul, the thought is that timing for the radio can come as part of 1588 running over OTN. All of this still requires a lot of development, and deployments are just starting. So we still have a lot to learn in this area. But network slicing is an important concept that OTN is looking to enable. So when we talk about 5G, there are essentially three important use cases. One is the enhanced mobile broadband, which is a better 4G. And the way they sort of look at doing that is by keeping the radio unit with the RF and PHY. Some of the PHY processing happens in the DU, and the radio link control happens here. And some of the other functionality before we get to IP happens in the edge, right? So this is essentially thinking of providing you higher bandwidth with HD video and augmented reality, virtual reality type of gaming. This is one use case which is very human-centric. There is a machine-centric use case, which is a very difficult use case, where all the functionality or most of the functionality really happens at the access nodes, and most of the computing also is at the edge, right? This is essentially where you need ultra reliable, low latency communication, URLLC, like it's called. And this is for things like self-driving vehicles, remote industrial control. So this is what I was talking about when you need low latency and ultra reliability. You cannot be operating a large industrial machine with sort of either errors or with higher latency. The machine's already done something, you've not been updated on what it has done, you can't control it, right? So I think this is important use case. And then there is the IoT use case where the amount of data is small, but the scale is very large. So essentially everything at the access node becomes IP, and then it is just essentially a IP network, which has various elements of access and edge and core cloud in it, right? So to enable all of this, you can see that OTN, with its ability to carry multiple types of flexible traffic in the client mapping, can sort of serve all of these simultaneously. There is another different way of viewing network slicing, where essentially when you have to offer a service or a connectivity, you can offer it either at the DWDM layer or the OTN layer. Part of the service can be wireless, part of the service can be over a packet network, part of it can be over IP. This is sort of a multi-domain virtual network, and that's another way that you can sort of use the different things, but OTN is an important component in that for certain applications. We talked about OTN for private line services. What's very important here is the word premium services, because you have dedicated bandwidth. Your packet stream is not going to get interfered with another vendor's packet stream as it would if you were using a router-only network or only a packet-switched network. Obviously, in a packet-switched network, one customer's traffic occupies the entire pipe during till his packet is under transmission. So your packet, even though it may be highly critical, can be stuck behind some other vendor's jumbo packet, right? So your packet will experience jitter, and there are buffering issues in packet networks that can also cause loss and delay. And none of that really is there if you get an OTN private lease line. So that's where a lot of our operator customers like OTN as the underlying technology to deliver these premium services. So really, I think I'm about 40 minutes in. So OTN-based transport networks have been sort of widely accepted by the operator community. They offer capacity, large capacity, and low latency, and the benefit of carrying with great amount of fidelity various types of signals, be it fiber channel, be it Ethernet, be it CPRI, be it some proprietary encrypted signal. It doesn't really matter, right? You can carry all of those signals in the appropriate size of the OTN container. And today we can do 50 millisecond protection switching at OTN. And we talked about the various GMPLS-based restoration schemes that are available once the primary and the backup path both have failed. Encrypted services ensure you secure services, and OTN gives you the premium services. With the multiplexing and the flexible size container, you can do this hard network slicing and reduce the amount of traffic that needs to be switched by the router. So I think overall, these are the things that I had mentioned in the use cases. And I'd just like this to be the key takeaway slide, that OTN is here to stay. OTN has been deployed very widely, and we are happy to engage with anybody who wants a deeper dive into this, into OTN. And I think our marketing team at Tejas is always eager and always willing to support queries from anybody. So please do reach out to them. Hema, I think that's the end of my talk. I can blank my screen, or I can stop sharing and put up my video. Should I do that?
Yeah, KJ. Thanks a lot for this very informative session. So we can move over to a few questions. So the first question that I have here is, why do we say OTN network should support 1588 for PTP when OTN is client transparent and transmits all the information from GPS to base station directly?
Yeah, so the issue is not so much the need for OTN to support PTP, but in order to support a high fidelity of clock recovery by the end client, the underlying transport network needs to make sure that the jitter performance is not too high. And that's the role that OTN plays in the entire scheme of timing. It is not just enough to say that, okay, I have a PTP that was in the core of the network and the PTP signals are recovered. If the underlying intermediate network has a lot of impairments, then clearly the kind of strict timing requirements that are there in 5G, because the 5G timing requirements are a lot more stringent than the 4G timing requirements, because they are looking at very fast handoffs. They are looking at various other modes of handoff between different types of radios. So the timing quality of the recovered time is very important. And that's where I think the OTN signals with its dedicated bandwidth per sort of connection are superior to the statistically multiplexed way that a PTP signal would be carried. Yes, you can give it higher quality of service, all of that, but if your PTP signal arrived at a router and the router was in the middle of transmitting a large frame, there is nothing that you can do to abort that frame and send the PTP signal instead. So time multiplexed infrastructure like the kind that OTN provides solves that problem.
So the next question that I have is, what is the advantage of bulk encryption to client encryption?
That's a good question. It's really a issue of complexity, and in terms of managing all the different key exchanges. Essentially, in the case of bulk encryption, what you are sort of relying upon is that at the two ends of a DWDM link, because internally, if it is optical and you can have amplifiers and ROADMs, you really don't need to do any reconstruction of the signal. So if you have a point-to-point link, then and you have a lambda worth of traffic, then bulk encryption is a cheaper solution. I mean, it's also a matter of cost. When you have to do a lot of encryption at different OTN levels, then essentially the structures you need in your product to do those simultaneous encryptions cost more than what the bulk encryption does. So, I mean, fundamentally, there is, one would think that client encryption is always superior had it not been the issue of cost.
The next question is, if an operator already has an OTN network with other vendors and is looking at adding Tejas nodes to its networks, do you perceive any challenges with regards to interoperability with these other vendors?
No, so that's primarily the reason. So I think what used to happen, I'll give you a little bit of a history. The same problem was there even in SDH, where there is, by ITU standards, if you have an SDH link and the other vendor also has an SDH, supports SDH, and you support SDH, it should interoperate. Where things started to fail is when vendors used some of the undefined bytes in the overhead to do proprietary communication. That obviously does not work when you have another vendor's equipment. So unless the other vendor allows you to be transparent to that. But if they are using the same undefined bits for their communication, then something's got to break. OTN sort of took care of that with respect to the better definition for the tandem connection monitoring. So as long as you respect your domain, you are fine. The next level monitoring can be done at a higher layer in the tandem connections. So I don't think that's a problem anymore. We have, I would have to check with our team whether we have interoperated with other vendors' equipment, because we have quite a large number of deployments with in operators' networks with OTN. So I don't foresee this as a challenge, but Hema, if you can find out who the specific person whose concern it is, we can get back to them with some more information of what interoperable, what vendor interop we have already undergone.
Yes, KJ, I've made a note of it. The next question is, what are the different mapping techniques of data into OTN frame?
That's quite a large amount of work. So there are different types of mappings in terms of GFP-based mapping and other type of CBR mappings. I don't think it'll be easy to explain that without a whiteboard, but you can look it up. It's all there in the standard. Primarily, the two techniques are GFP-based and byte-based for CBR.
We will pick up one last question, and this is, okay, Ethernet-based access networks seem very popular. How does OTN-based networks work with private line services?
Okay, so I think that's a very good question because there is the Metro Ethernet Forum, which has sort of standardized Ethernet services as E-line, ELAN with the constructs that they have, right? But most of the attributes in the E-line, ELAN service are based on gross parameters like the committed bit rate and the excess burst size, those kinds of parameters. Your service can be delivered within those and within those constraints, but there are some applications where, especially in client server mode, where essentially, or in a certain applications where you may want the messages to be as per you were running in a LAN, right? So what happens in a LAN is you have very deterministic communication. Now, if one server is located in one office and the other is in the other office, the attributes going across a packet-based network, like I said, get affected by other services running in the network. So essentially, I made a reference to it that on a packet network, let's say a 10 gig link, customer A's packet will occupy the entire 10 gig for the time that its packet is being sent out. This is in contrast to OTN, where let's say in a 10 gig OTN pipe, if you had, let's say 4 2.5 gig OTU ones, all of them are being serviced concurrently. right? A byte of this, a byte of that. So all services make progress. So as opposed to one service making progress for a certain time, then the next, then the next, then the next. That's what happens in a packet network. In an OTN network, all services are making progress at the same time. So you have a lot more determinism in terms of the packet delivery. So you will not introduce added jitter and latency. And if you're so for example, one can say I have 10 requests. I can choose to send one, wait a little while, send another, send another. If that is the way my requests go and that's the way my responses come, in a packet network, I put in 10 requests. There is no guarantee that all 10 will not be bunched up in one burst and delivered all at once. You'll still be meeting the CBR and the other parameters, but it's not the same. So for high fidelity connections where you don't want to lose any sort of information in terms of arrival times, OTN-based premium Ethernet services are better. The customer doesn't want to, the customer says it works in my LAN, but when I put it across the WAN, it doesn't work, right? You don't want, as an operator, you don't want to be getting into and trying to debug those problems because you'll have to have access to what the customer wants to do. The customer may not want to share that. And so there'll be a lot of back and forth in terms of making sure that the end applications work. OTN sort of makes it a little easier in that respect.
Thanks, KJ. And thanks everyone for joining this live session. Have a great day, everyone.
Thanks everybody for taking the time. I really enjoyed talking to you.